Have you ever wondered if there might be more dimensions to our universe than the three we know? This query leads us to the intriguing realm of the Braneworld theory. This theory, pioneered by Lisa Randall and Raman Sundram, ventures beyond the familiar three dimensions of our universe into a higher dimensional space, aptly called the bulk. Imagine a ship sailing across the vast ocean. This ship, in our analogy, is a brain, a three-dimensional membrane navigating through the bulk. But here's the catch. Our ship isn't alone. The bulk is teeming with a multitude of these brains, each representing a distinct universe. Mind-boggling, isn't it? But it doesn't end there. The Braneworld theory also suggests these brains could hold the key to explaining a puzzling phenomenon in physics, known as subatomic asymmetry. This asymmetry is like a cosmic puzzle piece that just doesn't seem to fit into our current understanding of the universe. The Braneworld theory proposes that the answer might lie in these extra dimensions hidden away in the bulk, and if that's not enough food for thought, some variations of the Braneworld theory speculate that these brains could collide, sparking the creation of entirely new universes. Imagine a cosmic collision birthing an entirely new cosmos. It's like the plot of a science fiction novel, but it's a theory taken seriously by some of the sharpest minds in physics. However, as with any theory, the Braneworld theory faces its fair share of challenges. The main hurdle lies in its testability. Concrete evidence for the Braneworld theory is yet to materialize. Some physicists believe that the behavior of black holes and precise gravitational wave measurements could offer potential avenues for verification. But until we can test these ideas, they remain just that, ideas. While the Braneworld theory is fascinating, it's not without its challenges, particularly when it comes to testability. So while we continue to marvel at the possibilities, we must also continue to scrutinize, question, and test, because that's how science advances. Newton's gravity theory has been a cornerstone of our understanding of the universe, but what if it's not the whole story? That's the question Mordechai Milgrom posed when he proposed the theory of modified Newtonian dynamics, or MOND for short. Milgrom's theory turns the concept of gravity on its head. Instead of being a constant force, MOND suggests that gravity behaves differently at lower accelerations. This idea stems from the inconsistencies observed when Newton's laws of gravity are applied to larger cosmic scales. The introduction of dark matter was an attempt to reconcile these discrepancies, but Milgrom proposed a different solution. MOND proposes that at cosmic scales, gravity's influence weakens more slowly than what Newton's laws would predict. This subtle modification could explain the behavior of galaxies without the need for dark matter, a substance that has yet to be directly detected. But the intrigue doesn't stop there. Building on Milgrom's work, Tom Zlosnik and Konstantinos Skordis developed RealMOND, an extension of the MOND concept. RealMOND incorporates an omnipresent field into general relativity. This field behaves like dark dust, providing gravitational heft without relying on undetectable particles. This approach to understanding gravity is intriguing because it challenges the conventional wisdom that dark matter must exist. It also offers a possible explanation for why, despite extensive searches, we haven't yet found any direct evidence of dark matter. The intrigue surrounding MOND and RealMOND is further fueled by recent studies that have detected evidence supporting MONDy in disk galaxies. These findings cast doubt on the necessity for dark matter particles and have reignited interest in MOND. The ongoing debates and investigations into MOND and RealMOND remind us that our understanding of the universe is always evolving. The lack of recent progress in dark matter detection and emerging evidence of potential external fields have prompted a potential re-evaluation of gravitational theories on cosmic scales. With the mystery of modified Newtonian dynamics yet to be fully unraveled, one thing is certain: our quest to understand the cosmos is far from over. What if we told you that space-time might not be just a framework, but a tangible, dynamic substance? This provocative question invites us to explore the work of Stefano Liberati and Luca Macchione. They propose a radical reimagining of space-time, not as an abstract concept, but as a superfluid substance with zero viscosity. Now, you might be thinking, superfluid, what's that? Well, superfluids are materials that, at extremely low temperatures, exhibit a host of unique properties. These include the ability to flow without any resistance, hence zero viscosity. They're the superheroes of the fluid world, defying normal behavior to perform feats of physics that boggle the mind. So what if space-time were a superfluid? Liberati and Macchione suggest that this could lead to some fascinating possibilities. For instance, superfluids, due to their zero viscosity, are known to break up into tiny vortices. If we apply this to our superfluid space-time, these vortices could potentially serve as the seeds for the formation of galaxies. Imagine that entire galaxies with their billions of stars might have sprung from microscopic whirls in the superfluid fabric of space-time. But why does this matter? Well, viewing space-time as a tangible, dynamic substance could fundamentally change our understanding of the universe. We're used to considering space-time as a backdrop, a stage upon which the drama of the cosmos unfolds. However, if space-time is a superfluid, it's not just a passive observer. It's an active participant in the cosmic dance, shaping and being shaped by the events that occur within it. This theory is, of course, still in the realm of speculation. However, it serves as a compelling reminder of how much we still have to learn about the universe and our place within it. Our understanding of the cosmos is continually evolving, and theories like this one keep pushing the boundaries of what we think we know. The superfluid space-time theory introduces a new, tangible understanding of space-time, challenging our conventional conception of the universe. Have you ever pondered over why the laws of physics are just so, and not any different? This question leads us into the debate over cosmic constants, the fundamental parameters that govern the laws of physics. These constants determine the strength of forces in our universe, from the speed of light to the strength of gravity. One perspective is the anthropic theory, which contends that these constants are not arbitrary but finely tuned. It suggests that even slight variations in these constants could result in a universe where life as we know it is impossible. Imagine if gravity was just a touch stronger. Planets might be too dense, crushing any life form before it could even begin. Or if the speed of light was slightly slower, the energy output of the sun could change dramatically, possibly freezing or scorching our planet. This theory implies an almost poetic balance, a cosmic harmony that permitted the emergence of life. It proposes a universe that is not indifferent but delicately calibrated to accommodate us. However, critics of the anthropic theory caution against anthropocentrism, the belief that human existence holds a special or privileged position in the universe. They argue that attributing such significance to our existence could bias our understanding of the cosmos. Perhaps these constants are not fine-tuned for life, but life has adapted to the constraints these constants provide. Maybe in a universe with different constants, life could emerge in forms we cannot even fathom. This debate between the anthropic theory and its critics is not just a scientific argument, it's a philosophical discussion, a deep dive into the nature of existence and the universe. It questions our place in the cosmos and explores the conditions necessary for life. Whether you subscribe to the anthropic theory or not, the debate over cosmic constants certainly raises profound questions about the nature of our universe and the conditions necessary for life. In the end, cosmic constants remain a fascinating mystery, a testament to the complexity and wonder of our universe. What if everything you know, everything you see, is nothing more than a holographic projection? This question brings us to the mind-bending concept of the holographic universe theory. Imagine a hologram. It's a flat, two-dimensional surface that, when illuminated from a certain angle, projects a three-dimensional image. Now, take that concept and apply it to the entire universe. This is the crux of the holographic universe theory. It proposes that our seemingly three-dimensional reality is actually a projection from a two-dimensional surface. This idea is not as far-fetched as it sounds. It draws inspiration from the principles of holography and physics. In a hologram, all the information needed to create a three-dimensional image is encoded on a two-dimensional surface. In the same way, the holographic universe theory suggests that all the information needed to describe our three-dimensional world is encoded on a distant two-dimensional boundary. The entire universe, with its complexity and depth, is therefore considered a holographic projection. Every star in the night sky, every mountain, every atom in your body, all could be projections from information stored on a far-off two-dimensional surface. But where is this two-dimensional boundary? Some theorists suggest it could be at the very edge of the universe, billions of light years away. Others speculate it could be in a completely separate, parallel universe. While the holographic universe theory is undeniably abstract and difficult to prove, it provides a new perspective on reality and our understanding of the universe. It challenges our perception of space and time, pushing us to think beyond our everyday experiences. But what does this mean for us? Well, on a practical level, not much. Our daily lives would continue as they are, regardless of whether our reality is three-dimensional or a holographic projection. But on a philosophical level, the implications are profound. It forces us to question the nature of reality and our place within it. While the holographic universe theory is mind-bending, it's another testament to the incredible mystery and complexity of our universe.